Okay, let's dive into this. Everyone says 16 gigabytes of RAM is basically dead if you want to run serious local AI. But in today's explainer, we are proving them wrong. We are attempting an absolutely impossible challenge, forcing a massive 19 gigabyte AI model into a tiny 16 gigabyte machine. I'm talking warning lights flashing, system crash alerts completely imminent. That is the exact level of stress we're putting this hardware under today, just to see if we can totally break the rules of what's possible.
So just think about what we're working with here. You've got this massive, glowing 128 gigabyte big boy workstation. Now, that is the kind of heavy-duty iron you'd normally need to run a powerhouse model like the newly released Qwen 3.5 smoothly. But then there's the completely unassuming 16 gigabyte Mac Mini. This is a true David versus Goliath scenario, guys. We want to run this cutting-edge 9 billion parameter model perfectly on that tiny little machine.
But right out of the gate, we hit a massive roadblock, 19.3 gigabytes. That is the sheer size of the uncompressed, unquantized version of this AI model. And trying to fit 19.3 gigs of raw data into 16 gigs of unified memory, well, it's literally like trying to pour a gallon of water into a pint glass. It's just not going to fit. So we've got to find a way to shrink it down.
And this brilliantly illustrates exactly how we start to tackle that problem: compression. To the human eye, an uncompressed image and a compressed image often look completely identical, right? But the uncompressed version takes up 14.6 megabytes of space, while the compressed one is a tiny 1.8 megabytes. It's drastically smaller. And here's the kicker: we can apply this exact same logic to large language models.
When we compress an AI model, which is a process called quantization, we are essentially crushing the model's weights, that vast ocean of numbers that literally make up its digital brain. We can take that massive 19.3 gigabyte model and squash it down to 10 gigs at 8-bit, or even a highly compressed 4-bit version at just 5.98 gigabytes. Now, looking at that 5.98 gigabyte number, you'd probably think, awesome, victory, we definitely fit it in the Mac Mini. But honestly, that is exactly where the real nightmare begins.
Because the model weights aren't the only thing eating your RAM. You've got to meet the hidden villain of our experiment, the KV cache. Think of the KV cache as the AI's short-term memory. When you feed an AI a super long prompt, it doesn't reread the entire conversation from scratch every single time it generates a new word. Instead, it stores these mathematical summaries, called key-value pairs, of every single token it reads. And as your conversation gets longer, this cache silently and aggressively chomps up your system memory.
And how aggressive are we talking? Well, if we take that exact same model and crank the context length all the way up to handle a massive document, the RAM usage instantly skyrockets to a staggering 92 gigabytes. And that's before we've even typed a single prompt. 92 gigs. Yeah, that instantly crashes our 16 gigabyte Mac Mini dreams right into the dirt.
So the core issue becomes pretty obvious. The model weights stay the exact same size once loaded, but that pesky KV cache grows massively until it completely dominates the system memory. And standard quantization, it only shrinks the weights. It does absolutely zero to stop the KV cache from devouring your RAM. So to survive this, we desperately need a secret weapon, a super compression tool for the cache itself. Enter Turbo Quant. Turbo Quant is amazing because it works directly on the KV cache. It functions almost like a giant digital hydraulic press, just crushing those huge blocks of memory data down into tiny, super efficient cubes. But how do you actually apply it? Well, the KV cache is made of K keys and V values. So what happens during our first attempt when we use Turbo Quant symmetrically? Meaning, what if we aggressively squash both the K and the V parts of the cache equally at the exact same time?
Well, initially this was a total disaster. The AI just spit out garbage. That is a direct quote from the source testing. Pushing the compression too aggressively on both sides simultaneously completely destroyed the AI's logic. It's kind of like compressing an image so much that it just turns into a useless blur of pixels. The model completely lost its mind.
Now, what's really interesting about this slide is just how badly it failed. To measure AI recall, researchers use a needle in a haystack test. They literally hide a specific secret fact deep within thousands of tokens of text and ask the AI to find it. Well, with the Symmetric Turbo 2 and Turbo 3 approaches across large 8K and 16K contexts, 0 out of 3 secrets were found. It was a catastrophic failure. Imagine a digital search beam scanning through a mountain of text and finding absolutely nothing.
But then came the pivot. A developer named Tom told us we were doing it wrong and suggested a brilliant secret weapon workaround. Instead of crushing both sides equally and destroying the data, we switched to an asymmetric approach. Step 1. Use a lighter, standard 8-bit quantization for the K layer to maintain its structural integrity. And step 2, Apply that heavy, super aggressive Turbo 3 compression only to the V layer.
And the results of this asymmetric pivot? Absolute, resounding victory. Across the board, from 1,000 all the way up to a massive 32,000 tokens of context, the AI perfectly recalled every single hidden secret. 3 out of 3 found, a 100% success rate. The intelligence and logic were totally restored, but the memory footprint stayed incredibly small.
Which brings us to the ultimate climax of this explainer. Armed with this clever asymmetric Turbo Quant setup, we pushed the unassuming 16GB Mac Mini to its absolute limit. It didn't just run a standard prompt. No, it successfully processed a massive, towering mountain of text, 131,000 tokens. Imagine a digital search beam scanning through a small novel's worth of data, all locally on an entry-level machine, without crashing.
So the crucial point is not only did the standard uncompressed version crash instantly at this size, but with Turbo Quant, the Mac Mini didn't just barely survive the payload. It comfortably ran a 131K context window with 3.6 gigabytes of RAM to spare, literally glowing in green. We actually have room left over on a machine that was supposed to be completely obsolete for this task. No way, right?
Let's move to and see how this builds, because fitting it into memory is only half the battle. What about speed? On powerful chips like the M5 Max, Turbo Quant isn't just smaller, it completely changes the performance curve. The Q8 baseline speed drops off a cliff as context grows, falling to 37 tokens per second. But Turbo Quant, it maintains a blazing fast, flat speed of 44 tokens per second. Because the KV cache is so small, it completely removes the memory bottleneck.
On machines where memory bandwidth is the biggest hurdle, this super compression is an absolute game changer. It makes running massive, locally hosted models a reality for the average user without needing some massive server rack. The 16GB Mac Mini didn't just survive, it actually beat the baseline. 16GB feels really different now. Which leaves us with this final electrifying question. With software engineering this clever, is 16 gigabytes actually dead? Or, thanks to tools like Turbo Quant, is 16 gigabytes the new standard for local AI? Think about that next time you're checking out hardware specs. Thanks for joining me on this explainer, and I'll see you next time.